Hi guys, welcome to Conceptual Science YouTube channel. This is Ehsan Danish. Today I'm going to solve a numerical problem which is about infinite square well, which is basically one-dimensional infinite square well in which quantum particle can move in one dimension from some point to another point, right? So the problem is which is displayed in the screen is that question number 2 of chapter number 1 of the graphics books, the introduction of quantum mechanics. So the statement of problem is just like that: a particle of mass m moves in a one dimensional box of length a with boundaries at x is equals to 0 and x is equals to a. Thus the potential is given that uh, in that finite square well is 0 for the boundaries from 0 to a. X is equals to x is the basically length of the infinite square well from 0 to a, and potential will be equals to infinity elsewhere, means without outside the infinite square well, uh, excluding from 0 to a, the potential for the particle is equals to infinity. The normalized wave functions of Hamiltonian for this system are given by normalized wave function for a particle which is moving in infinite square well is this, and the available energies for that particle in that infinite square well is given by this equation. So first of all we talk about the infinite square well. Basically infinite square well is nothing but it's a square type box in which a quantum particle can move within restricted limit, right? So this is the first boundary which I called O, sorry, 0, and second boundary is A, sorry, second boundary is A, which I labeled as A. What's the problem? Sorry, A. So this is the infinite square well in which a quantum particle is moving. We call it infinite because particle cannot have much energy to go outside from this box. It a particle cannot gain too much energy to move from outside from this box. That's why we call it infinite square well. So this is the center point of infinite square well. This is center point of infinite square well, which I labeled as a upon 2, a upon 2. So this is the mid point, center point of the infinite square well. Secondly, according to the question, we are to find the energies or probability of the finding particle from 0 to a equals to a upon 4. So a upon 4 is this, which I am going to drawing, which I am going to draw. This is just like a upon 4, which I am going to label a upon 4, right? So basically we are asked to find let's suppose this is the infinite square well in which the potential for the particle to exist inside the infinite square well is 0 equals to 0, and outside the box is the potential will be infinity. We and from V is equals to infinite, right? Infinite. And here also from outside the box, the potential is also equals to infinite, right? So according to question, wave function is given here. This is the wave function, which is the basically wave function of the particle, which is moving from 0 to a boundaries of the given infinite square well, and this is the required available energy states for that particle inside the infinite square well, where the quantum number n, which is given in energy formula n square, to n is representing that n can be values from n is equals to 1 2 3 etc. So first part is that assuming that particle in an eigenstate, let's suppose the particle is an eigenstate which is represented by psi n of x. Calculate the probability of the particle is found somewhere in the region 0 x greater than or equal to 0 and x is equals to less than or equals to a upon 4. Show that this probability is depending on n. Basically we are asked to find the probability of the particle to find in between from 0 to a upon 4. Basically particle is moving from a to 0 to a, but how much, what is the probability of that particle to find in this required region, which is basically from 0 to a upon 4, right? So actually we are asked to derive some equation which is basically showing, which will be basically showing that the probability of the particle is depending upon the number of n, which is the number of eigenstates, right? So we are going to do first part. What will be the first part? The first part is that the wave function of the particle is given by psi of x is equals to under root 2 upon a sine n pi x upon a, which is given in question. So we are to find the probability of the particle from 0 to a upon 4. So lower limit will be 0 and upper limit will be a upon 4, which a is the second boundary of the infinite square well. So we are to find the probability of particle in the region from 0 to a upon 4. So probability will be the square of wave function. Wave function is this, and we have taken square and dx. So we are going to integrate this probability wave function in the region from x is equals to x greater than or equal to 0 and x less than or equal to a upon 4 is equals to probability at this region is equals to a 2 upon a. Basically 2 upon a, here is whole square, which cancel with under root. That is why 2 upon a is taken out from integral sign. Integral 0 to a upon 4 sine square n pi x upon a into dx. So next the integration formula, sine square x is sine square theta is equals to 1 minus cos square theta upon sine square x, sine square theta is equals to 1 minus cos theta upon 2. So we have applied this formula here, and a upon 2 integral from 0 to a upon 4 1 minus cos 2 n pi x upon a and theta. This is basically angle 2 n pi x upon a is angle, and divide by 2 is we have converted sine square into in terms of double angle of cosine theta. This is basically formula. So we can take common 1 upon this 2 from outside the integral, which is taken here, integral from 0 to a upon 4, 1 minus cos 2 into n pi x upon a dx, right? So 2 cancel, 1 upon a bracket from 0 to a upon 4 dx. Basically we have multiplied this integral sign with 1 and this cosine function separately. So 1 is here, integration of 1 into dx minus integration of from 0 to a upon 4 cos 2 into n pi x upon a dx, right? So the integration of 1 is x within the limit from 0 to a upon 4, and integration of cos 2 n pi x upon a is equals to sin 2 n pi x upon a, and a derivative of this angle is taken in denominator, which is n 2 n pi upon a. Derivative of x is 1, right? These all terms is constant term, that is why this is taken as it is, and the derivative of x is equals to 1, and the limit is from 0 to a upon 4. So here we are going to put the limit at x equals x, the upper limit a upon 4, lower limit which is equals to 0 we cannot write here. Next, minus sign. In this equation a upon 2 n pi x is a constant which merging in which I am converting from denominator to numerator, and numerator to denominator, that can be written in this form, right? Sin n pi, sin 2 n pi x upon a, 4a, right? So a and a are cancelled. Actually this whole is angle, 2 1 the 2, 2 2 the 4, a or a cancel out, so we left with a upon 4, 1 upon 4, 1 upon 4 minus 2, 1 upon 2 n pi, put n equals to 1. So this is the basically equation. Note that we have started with p is equals to, right? P is equals to this, p is equals to this, p is equals to this, p is equals to like, p is equals to this. This is the equation of probability of finding particle in the region from 0 to a upon 4. So this is the equation for the particle of probability finding in between 0 to a, and which is totally depending upon the number of value of n. If we put n is equals to 1 in this equation, we get the probability 0.0908, which is equals to 9% of 1. Similarly we can put n is equals to 2 here, n is equals to 3, n is equals to 4, n is equals to 5, etc. You can put from value of n, which is equals to from 1 2 3, etc. n cannot be 0 for the particle in infinite square well. So as we put the value of n like this formula gives the probability in this way. So the maximum probability is the probability which is at n is equals to n, right? Now second part was, for what value of n is there the largest probability of finding particle in 0 to a upon 4. So the largest probability we have noted here. We have used the probability equation which we derived here, and using this equation we have put it some values of n like 1 2 3 4. This equation gives the corresponding probabilities for these n values like this. So as we are going to put the values of n from 1 to higher, the probability will get maximum. So the largest possible probability is at n equals to n, right? So this is basically we have solved two parts of that problem, part number A and part number B, and inshallah part number C will be discussed in next coming videos. Today that's enough. Thank you so much.